Good morning everyone, welcome to today's worked exam answer video. Today I'm having a look at a rate equations question which could appear on paper 2 or of course paper 3. This one is presented in a bit of a different way for the first part of this question, which is why I chose this one, because it takes a little bit more thinking about than when we only have the initial concentrations given to us in like a table of kinetic data. We've got to work out the initial rates, we've then got to work out the orders, and then there's a question on the back where we're going to work out a value for K. So we're told that substances P and Q react in solution at a constant temperature. The initial rate of reaction was studied in 3 experiments by measuring the change in concentration of P over the first 5 seconds of the reaction. So normally in the tables you would get experiment 1, initial concentration of P, initial concentration of Q, initial rate of reaction, sorted. Looks a little bit weird because we've got for P and Q a row for time after mixing, so initial concentrations, and then the concentration after 5 seconds for P. They didn't measure it for Q, only for P. And it's that kind of change in concentration over time that we're going to need to work out to get rate. And I know when I first looked at this question I was a bit stumped. The layout threw me a little bit, and I know the same can be said for students that have attempted this as well. But the key thing that we need to come back to is what rate of reaction is, like how we would define it. So we're measuring the change in concentration over time. That's the units for rate, concentration per second, change in concentration over time. And I think it's helpful that they gave us the first or rather the initial rate for experiment 1, so that we can check kind of how to get to that. So that's the first thing I'm going to kind of show you. So change in concentration over time, well, how does the concentration of P change in experiment 1? So we're going to do 1 times 10 to the minus 2 take away 0.92 times 10 to the minus 2. That's the change in concentration of P. And then we're going to divide that by the time, which is 5 seconds. And when you do that, you get your answer to be 1.6 times 10 to the minus 4. So that then shows us what we're going to need to do for the next 2. So to work out the initial rate for experiment 2, we would want to do the initial concentration of P, 2 times 10 to the minus 2, take away 1.84 times 10 to the minus 2 to get the change in concentration, which is 1.6 times 10 to the minus 3. Then we divide that by 5, because that's the time period over which the concentration has changed, and that gives us an initial rate for experiment 2 of 3.2 times 10 to the minus 4. And then we can do the exact same thing for experiment 3. How has the concentration of P changed over the first 5 seconds? It's changed by 1.6 times 10 to the minus 3 divided by 5, and the initial rate has stayed the same as in experiment 2. Now you only get 1 mark for that, and I think that's a little bit harsh because there's a bit of extra thinking that needs to be done in order to figure out how to measure the initial rate. But like I said, by definition, rate of reaction is the change in concentration of a product or reactant over time. So, and the units also a little bit helpful there. The other reason why I feel like that's harsh is because you also won't be able to do the next question if you couldn't do the initial rates, because now we're going to find the order with respect to P and with respect to Q. Now we're going to have to do this in exactly the same way that we normally would, even though the information is presented in a little bit of a different way. So it's up to you how you want to do this, but we're going to now need to ignore the concentrations after 5 seconds that we were given for P. So it might be helpful just to, and you might not want to do this obviously in the exam, certainly not in pen, in case you want to come back and check your answers. But just cover those up, get rid of them somehow. You could do it in pencil obviously, and then you could rub it out. And then what you might also want to do, and you might not need to, which is absolutely fine, is add the initial rates as another column so that you've got everything that you need as you would normally have it presented to you. Now, like I say, you might not need to do this, but I just thought I'd show it as an option. Okay, so now what we would do, as we normally would, is find two experiments where only the concentration of one of the reactants is changed, which is experiment 1 and 2. The concentration of Q has not changed between experiment 1 and 2. So what we can now do is look at, well, how has the concentration of P changed between experiment 1 and 2, and it's doubled. And then we can think about, well, how's the rate of reaction changed, which has also times by 2. That therefore tells us that the order with respect to P is first order, because what we did to the concentration of P was matched in the change in the rate. So P is first order. And now we can do the same for Q, except for Q, there are no two experiments where only Q is changing, which is fairly standard, to be fair, for these sorts of questions. So we're going to have to pick two experiments whereby Q changes, first of all. So we could use 1 and 3 or 2 and 3, and literally just because it's easier for me to draw my arrows, I'm going to pick 2 and 3. But we're also going to have to consider, between experiment 2 and 3, what's happening to the concentration of P, because that's changing and that's therefore going to have an effect on the rate. So 2 times 10 to the minus 2 divided by 0.5 times 10 to the minus 2, I believe, is 4. So we've divided by 4 to change the concentration of P between experiment 2 and experiment 3, and therefore the rate would be changed in the same way because P is first order. So we'd also then divide the rate by 4, and I'm just going to note down what that would give us. So 3.2 times 10 to the minus 4 divided by 4, which gives 8.0 times 10 to the minus 5. Which is not the initial rate for experiment 3. So that means that Q is not 0 order, because changing the concentration of Q is having an effect on the rate. So what do we need to then do to 8 times 10 to the minus 5 to take us, back to 3.2 times 10 to the minus 4? We're going to times by 4. Now what happens to the concentration of Q between experiment 2 and 3? That's been doubled. So by doubling the concentration of Q, we've got the rate to increase 4-fold. So therefore, because 4 is 2 squared, Q is a second order reactant. If anybody has any questions about what I just worked through there, as always, please do not hesitate to let me know. I know these tables can be a little bit faffy, particularly when both concentrations being changed at the same time. But for the reactant that you know the order for, which for us was P, you have to first of all see how the concentration of P is changed and use that to figure out what only changing P would do to the rate. Now I've coined this the intermediate rate, i.e. if we only change one reactant, what would the rate be? And if the rate is then the same as what it actually is, then the other reactant will be 0 order. If it's not, you can figure out how much more it needs to change and then see how the concentration of Q change is related to the change in the rate to figure out if it's first or second order. Okay, now for turnover, last question, we've got a different reaction. We're now dealing with substances R and S. So we are being told here that S, let me read that again, a reaction between substances R and S was second order with respect to R and second order with respect to S. Now, first thing I might do, as I've said in other videos, I'm a very visual person, is I might just write myself a rate equation, which I'm going to need to do anyway in order to work out what K is, but just after reading that first part of the question, I might just want to get it written down as rate equals K, and then it's second order with respect to R and second order with respect to S. Obviously you could have read the whole question and done that, but sometimes I feel like it helps to break it down and just write down what you can as and when you can during the question. We've then got the initial rate of reaction, so 1.2 times 10 to the minus 3 mol dm minus 3s minus 1. Initial concentration of R was 1 times 10 to the minus 2 mol per decimeter cubed, and the initial concentration of S was 2.45 times 10 to the minus 2 mol dm minus 3. And we've got to calculate a value for the rate constant K and give the units for K. So first thing I would do after this is then rearrange the rate equation to get K equals. So K is going to be equal to the rate that we've been given divided by the concentration of R squared times concentration of S squared. Then I can sub those numbers in. So the rate of reaction we said was 1.20 times 10 to the minus 3. And then we're going to divide that by initial concentration of R, 1 times 10 to the minus 2 squared, times the initial concentration of S, 2.45 times 10 to the minus 2 squared. Then we can work out what that's going to give us. So let me pop that into my calculator. Now you can do this all in one go, which is what I'm going to attempt to do now, but you don't have to. So you could work out what 1 times 10 to the minus 2 squared was, then times that by 2.45 times 10 to the minus 2 squared, and then do your value for the rate divided by that. But you should, if you use brackets correctly, be able to put it in all at once, depending on what type of calculator you've got as well. So that gives me a value for K of 19,991.7. Now we've been given our values to 3 significant figures, but if I gave such a big number to 3 significant figures, it would actually be 20,000, because we'd have to go for 19,900 and something, but then we'd have to round that up. So then it would become 20,000, which would look a bit odd because that would be unclear how many significant figures to go to. So I could do it as 19,992, but I'm going to leave it as I've written it there. So that's the value I can put here. Now in terms of the units, we know the units for rate and we know the units for concentration. Now I'm normally a big fan of writing out mol dm minus 3 s to the minus 1, and then how many mol dm minus 3s we've got on the bottom, which in total is going to be 4 of them. Now it might be that you're happy to not write out the units, but just kind of do a bit of a tally of I've got 1 mol dm minus 3 on the top and I've got 4 on the bottom, so therefore I can cancel one of them with one of the ones from the bottom, and that's then going to leave me with 3 on the bottom and then the s minus 1 on the top. So then we would gather together the moles and the dm minus 3s, so it's going to be s minus 1 over mol cubed dm minus 9. And then when we bring the bottom part of our fraction up to the top, we have to flip the signs of the 3 and the minus 9 to minus 3 and plus 9. So it's going to be moles to the minus 3, so that's 1 over mol cubed, dm to the plus 9, and then s to the minus 1. And don't forget that when you're doing the units for the rate constant, because they're never going to cancel. So got to remember to keep your s minus 1 in there. Okay, hopefully that all makes sense, both that question and the previous 2 parts as well. But any queries, please let me know. Any requests for videos, please let me know. I might be able to do another before paper 2, and then my hope is to do some more for paper 3 as well. All the best with your revision, guys. Please don't hesitate to ask if I can help in any way. Take care of yourselves, and I wish you all the best for paper 2 and 3, just in case for whatever reason this is my last video before then. Good luck everyone, take care, bye.